afterwards. So I'm very, very happy to welcome you back to another webinar in our Beyond PFAS series, and so many of you today. Really interesting. So today's webinar is not addressing any specific use, but a material that is present in a large part of the applications, and this is fluoropolymers. So the PFAS restriction dossier submitters, they took a very clear stand when they included fluoropolymers into the scope, as they do fall under the definition, and that we cannot solve the PFAS problem without addressing these materials. And we have already talked about this before, but there are some strong misconceptions around fluoropolymers. And one was straightened out by the OECD earlier this year, that there is no definition of polymer of low concern. And there is also no ongoing work on creating such a definition. And any such claims are simply not true. There is also a misleading narrative that we cannot make the green transition happen without fluoropolymers. I'm sure you've all heard this. While there are always uses to be worked on, we also see that there are a number of alternative materials with similar properties as fluoropolymers, different properties for different materials. So fluoropolymers, they have many functionalities, and therefore they are used in a broad variety of applications, from consumer to industrial use, which is challenging when looking for alternatives. And there could be further clarification on where in the life cycle of fluoropolymers we see the biggest emissions, but in the bigger picture of it all, the production sites have never been able to not contaminate surroundings, the water sources, the soil, and the air. And as fluoropolymers are so diverse in their use, they end up in the waste streams with different problematic outputs, like PFAS spread from incineration. So today we're looking at how the alternatives side is moving ahead, where we can find the future materials that do not contribute to the PFAS pollution crisis. And with me today, I have three external panelists to shed light on this topic. It's Ian Keyte, Principal Environmental Policy Consultant at WSP. We have John Grassmeter, Chief Scientist at Victrex. And we have Emil Damgaard Møller, Chemistry Consultant at the Danish Technological Institute. And for the panel later on, we also have Dr. Hanna Holmqvist, Senior Toxicologist here at ChemSec, and she will also join later then. I am Teresa Schell, Head of Policy at ChemSec. So the recordings and slides from today's webinar will be made available. After the presentations, there will be an opportunity to ask questions to the panelists. So please note down any questions you have and write them into the Q&A box in Zoom, and we will do our very best to respond to them later on. So with that, I want to introduce our first speaker. It's Ian Keyte Bernard. He is Principal Consultant at WSP, where he's worked for 8 years. He has a background in environmental chemistry and has worked extensively on chemicals policy, including REACH and POPs regulation. Ian, please.
Thank you, Teresa. Hi, good afternoon, everyone, depending on where you are in the world. Nice to be talking to you today. Indeed, I'm from the Environmental Policy and Economics team here at WSP, and I'm going to be talking very swiftly about a project that we conducted for ChemSec earlier in the year, looking at PFAS alternatives in more challenging sectors, or the most important sectors.
Sorry to interrupt you, Ian.
Yes.
It would be great if you could turn on your camera. I don't think it's on.
I'm terribly sorry.
Thank you. No
there
problem.
You go. I'm
Thank
sorry.
you very much.
I don't know if everyone else is going to appreciate it, but there you go. That's fine. Hi, good afternoon or good morning to you, wherever you are. So yes, if you go to the next slide, please. in the very sort of time-limited nutshell that I'm finding myself in, I will quickly try and explain what this project was about and explain a little bit how this relates to what we're talking about today. So earlier at the beginning of the year, ChemSec commissioned us to conduct an investigation for them, a research project that looked to gather information and build a stronger evidence base about the availability and the feasibility and the safety of alternatives to PFAS in the most important sectors of use. So what that basically involved was collecting and collating information together about the identity of alternatives, be that substances, if that's a chemical drop-in replacement, or particular technologies or alternative materials, the trade names of products that are on the market and the companies that market those PFAS-free alternatives, looking at the specific sort of applications, the specific uses or the actual functions that those alternatives provide, and information about the availability and the feasibility of a technical or economic basis for those alternatives, and also collecting information about hazard data for those alternatives to get an idea about their safety. And particularly importantly, getting an idea about what the strength of evidence is about these particular alternatives, and particularly identifying where there are remaining gaps or uncertainties about those alternatives. Next slide, please. So first and foremost, it's probably important to explain a bit about what we considered in terms of what are the most important sectors in this particular context. So this is a plot that ChemSec put together a while back, which looks to illustrate or basically plots different sectors of PFAS use according to the volumes of PFAS that are being used and the availability of viable alternatives for those particular uses. So this was really to illustrate what actions need to be taken or what needs to be done in terms of development of safer alternatives. So there are certain uses for which substitutability is already very high, or there is substitution already taking place. Certain uses where there are some degree of alternatives available, but more action needs to be taken, for example, to scale those up in terms of their volume of use, and certain uses which are much more challenging, and actually developing sort of viable approaches needs to be looked at more closely. So in the context of our work, our focus here was really on this kind of middle section, this middle area here, where in terms of PFAS uses, in terms of the volumes of PFAS that are being used and their perceived importance in terms of their function or the actions that they provide in those uses is very well established, but there is some degree of uncertainty or a lack of information available about the viability of alternatives for those particular sectors. So that's where our main area of focus was with this particular area of work. Can you go to the next slide, please? So the four broad sectors that we focused on and we discussed with ChemSec and agreed to focus this work on were medical devices, so things like implantable or non-implantable medical applications, medical catheters, medical tubing, coatings used in medical devices, green energy, so a wide area of uses, including things like fuel cells, batteries, solar cells, wind turbines, and then also industrial uses and transport uses, so things like the wiring and cable insulation that's used in industrial uses or in transport applications, adhesives and seals that are used in industrial and transport uses as well as a much wider area of use for PFAS in those areas. So clearly, four very broad, quite complex sectors to try and grapple with in what was only a sort of 3 or 4 month research project. And that's not to suggest that other sectors are not important in this context as well. And there were other types of use that we considered would also probably fit this description as well. Things like construction products or lubricants or hydraulic oils are probably also fit this description. But we reflected on the fact that these are actually being covered in parallel projects elsewhere in other research. So we didn't want to duplicate what was being done with those uses. So that was not part of the investigation here. We focused just on these 4 areas of use. If you go to the next slide, please. So in terms of our approach to this, it's probably very important to emphasize what this project was and what it wasn't in terms of what we were doing. So really, the point of this work, it was a very old-fashioned kind of consultancy project based on desk research, based on literature review, a bit of additional consultation and discussion with expert stakeholders. It really was not a really in-depth technical assessment and looking at the real kind of sort of functionality or the chemical physical properties of particular alternatives relative to PFAS. Given the relatively short amount of time that we had and the broad context and the broad scope that we had to investigate, we realized that probably wasn't going to be very possible. So it was a very broad look, more from a sort of top-down market-based assessment of what type of alternatives are available on the market now. What are the sort of the pros and cons, or the limitations, or to what extent these alternatives can be used for these particular applications. And what we realized was, I think, and one of our key things that we really wanted to do from the outset of this work, given that we had 4 very broad sectors to focus on, where the number of specific uses and applications within those sectors is very broad, was to look for priority areas of use or priority uses within those sectors, and in particular areas of overlap or synergy between these 4 different sectors, where we can investigate the uses of PFAS and the potential for alternatives that cross-cut and sort of overlap across all 4, or at least most of those different uses. So we looked particularly at particular types of PFAS or specific PFAS materials that are common across all of these different sectors, and I think that was our main area of focus. So it's not surprising, therefore, that our focus fixed upon very quickly the use of fluoropolymers. It wasn't necessarily our intention to specifically look at fluoropolymers from the outset of this work, and it wasn't the only thing that we looked at across these different sectors in terms of PFAS use, but obviously, given that they are very applicable and widely used across all 4 of these sectors, quite a significant amount of our focus here was on the use of fluoropolymers. Go to the next slide, please. So with that in mind, we quickly highlighted that there were some common alternative polymer materials that are being used in place of, or certainly have the potential to replace or be used instead of, fluoropolymers. And there are a wide number of manufacturers and suppliers that are manufacturing these types of alternatives for products that are already on the market across all 4 of these different sectors. We've provided an overview of some of them on this slide here. This is by no means an exhaustive list. So the 3 main types of polymer alternative to replace fluoropolymers in these uses include things like PEEK, polyamides, and ultra-high molecular weight polyethylene, which I guess people on this call will probably be familiar with already. And these are alternatives that are highlighted in ECHA's Annex 15 restriction proposal report for PFAS, discussed more broadly from a sort of a generic replacement for fluoropolymer, rather than in the context of specific uses within these different sectors. So our job here was really to investigate the potential for these types of materials to be used in specific types of products within our 4 different sectors that we were highlighting. It's not necessarily suggested that these are materials that could replace all uses across these 4 sectors, given how broad they are. But our focus here was to look at specific examples or specific applications for which these materials could be used in. If you go to the next slide, please. I'm attempting here to summarize some key results from the work in one slide, which I hope you can appreciate is quite tricky to do, given that we have quite a lot of interesting observations from the work. But I think common observations, there were quite similar things that we noted across all 4 of the different sectors that were quite common across all of them. So try to summarize this as best I can here. So in terms of uses, yes, the sort of key usual suspect, fluoropolymers or fluoroelastomers, are cropping up as being used quite widely in different applications across all of these different sectors. And there are certain common areas of use or applications that are relevant across all of these different sectors. So, for example, cable and wiring insulation, adhesives and seals, like I already mentioned. And again, the sort of key properties and key uses that make fluoropolymers so popular in these types of uses are probably quite familiar to people in terms of things like their mechanical strength, their durability, their resistance to chemicals and heat and weather, their low flammability, and so on. So they're the things that we really need to try and replace with these types of alternative polymer materials. So we did, obviously, as I said, noted that things like PEEK and polyamide and ultra-high molecular weight polyethylene materials are being marketed and specifically being used across uses in these 4 different sectors, as well as a wider group of alternatives and other types of polymer materials that we've also noted in our work. And in terms of what these alternatives are able to do, we were able to investigate that and found that for quite a few different uses and specific applications within these sectors, there are types of properties and the types of performance that's needed across those types of uses are being met, or certainly can be met to some extent, by these types of materials. So in terms of the thermal properties, the resistance to chemicals, their mechanical strength, that dimensional stability, wear resistance, and then when it comes to medical uses, their biocompatibility, so their certification to be used in medical applications is something that we've highlighted here. And there were particular specific products for which these types of materials are being used that can potentially be used instead of a fluoropolymer. But at the same time, I think we do also have to reflect that there are quite significant limitations and other kind of uncertainties that we need to reflect on here as well. So they may not necessarily be useful or can be used for all types of applications within these sectors. And I think also given the fact that you have a lot of different specific functions within one particular product or one particular component that you need to try and replace at the same time, that makes that very tricky and a complicated process. And I think certain uses for which you would consider these to be critical applications, for example, where they relate to the safety of particular components or the integrity of particular products, obviously that's very difficult to replicate the kind of performance that you need. We also reflected on the fact that gathering cost data was quite challenging with this, and actually being able to carry out a very specific and detailed sort of comparison of the economic performance of different materials was quite tricky here. If you go to the next slide, please, I think we have a couple of very quick case studies to sort of draw out from this. From a couple of areas of these sectors that we looked at. So for medical devices, one thing we looked at was catheter tubes and coatings for those materials, for which again fluoropolymer is our main point of focus here. So expanded PTFE is used often in combination with FEP, and they have a number of different properties that they impart. Particularly their low friction and their smoothness is particularly important and a desirable property for these types of products. But again, we've seen that there are PEEK and polyamide-based products that are being marketed and used for these types of applications, and also non-PFAS-based coatings that can be used for these types of applications. And in many cases, they meet the required standards or the required functionality that's needed for those types of products. One particular example that we saw highlighted within this was their use in balloon catheters, for which these types of materials can be used. But again, that doesn't necessarily mean that these types of materials can be used in all types of catheter tubes within medical uses. And also, I think it needs to be taken into account that certain chemicals that we've seen used as alternatives need to be looked at in terms of their hazard properties a bit more closely, because some of them could potentially have PBT properties. If you go to the next slide, please. Another area that we looked at within this, obviously green energy, and one particular area within that was quite significant was lithium-ion batteries. So again, fluoropolymers are quite widely used for a number of different properties and a number of different components within lithium-ion batteries, again, because of a number of key properties that they impart, particularly their electrical stability, heat and chemical resistance, hydrophobicity, and flame retardancy, and their very good durability that you need to try and replicate. We highlighted in our work that there are a number of different PFAS-free lithium-ion battery applications that are being developed. I think they highlighted a couple of them on the slide here, and they are being developed potentially for use in a wide number of uses that these sorts of batteries will be used in, for example, in electric cars, trains, military applications, power tools, medical devices, and energy storage. But we did have to reflect at the same time that these are technologies that are not yet fully commercialized, and their availability currently is limited, and a little bit further work needs to be done to really demonstrate their viability for these types of uses, particularly to demonstrate their long-term durability, and also how these types of applications or types of alternatives could be used in other types of batteries, wider than lithium-ion batteries. Okay, I think I have one final slide to try and just draw out some final conclusions from this, because for every conclusion that we have, I think we have to balance out with some degree of a limitation, and also to highlight some remaining data gaps and areas for further work within this. So while the work that we've done with this does obviously demonstrate that there is a market for PFAS-free polymer materials and a number of non-PFAS based materials for these types of uses, and that market is clearly there and is expanding, and we've obviously highlighted there are a number of specific uses within the 4 sectors that we've looked at for which these types of materials can impart the types of performance and the types of properties that you need. I think we also need to reflect on the fact that it's obviously not an exhaustive or definitive study. It's only a relatively short-term consultancy project that we've worked on. And I think we need to reflect on the fact that the findings are based largely on publicly available information, and a lot of that's come directly from the manufacturers and the suppliers of these types of products. And given sheer number of different types of applications and types of uses within these types of sectors, and the number of specific functions needed within one particular component, it's obviously hard to demonstrate that these types of materials are suitable for all of them. In terms of areas of remaining data gaps in future work, again, given the complexity of these different sectors, there are still areas where actually the use of PFAS is still not fully understood, and that's obviously a prerequisite to being able to investigate alternatives, is to know where the PFAS are in the first place. And we've reflected on the fact that there needs to be more careful consideration about both the cost data and the hazard data around alternatives to be able to provide a better comparison. And I think we've really reflected on the fact that the type of information that's gathered from this can really help provide a start point for emerging data sharing tools and platforms to share best practice and information about what alternatives are available. So hopefully this can represent a good start point to really fully investigating these and understanding their potential in more detail. So I think that's everything from me, and I'd like to say a huge thanks to everyone in the WSP team who have worked on this, everyone at ChemSec who have been helpful for the project, and all the participants who provided information to the work. We appreciate that, and we appreciate the invitation to speak to you today. Thanks, Teresa.
Thank you so much, Ian. Very interesting presentation and an interesting report that you did for us. So. Very much appreciated. And I think it is a good starting point for this discussion. I would also like to take the opportunity to encourage everyone to post your questions in the Q&A box. You have already started. Just for your information, the earlier you put it in, the more likely it is that I will fish it out later and post the question to our panelists. So with that, we're going to take a closer look into one of these alternatives that Ian presented. So with me today, we have Professor John Grassmeter. He's a chief scientist at Victrex with over 30 years experience in the global polymers industry. And he is inventor and author of over 50 patents and literature publications. He's worked in R&D, application development, marketing and business leadership positions. And in 2005, John joined Victrex and is currently chief scientist. John, go ahead.
Thank you, Teresa. Thank you for the opportunity to present today. Hello, everyone. I'd like to introduce you to the world of PEEK and PAEK polymers. And in particular, I'd like to highlight how in some applications, these materials can be used to replace fluoropolymers. Now, the properties of Victrex materials are generally different to fluoropolymers, so they're not going to replace them everywhere. But what we are seeing recently is a lot of interest in many applications where they can. Can I have the next slide, please? So what are these polymers? Well, perhaps I should start by explaining the difference between PEEK and PAEKs. So PAEK, or polyaryl ether ketone, is the family name for this class of high-performance polymers. PEEK, on the other hand, as we know it today, was commercialized in the early 1980s. It is the best known and most widely available polymer in the PAEK family. There are many others, but only 5 or 6 have ever been commercialized. Today, I'm going to focus on PEEK. The polymer triangle you can see here summarizes where PEEK sits from a performance point of view. The top of the triangle, the darker colored high-performance polymers area, represents less than 0.5% by volume of all polymers produced today. The PAEK family represents about 1% of that small amount. In volume terms, we estimate the global installed capacity for PAEK polymers is currently around 20,000 tons per year. What sets PEEK apart is its unique combination of properties, some of which you can see here. Key among these are wear and chemical resistance, combined with an ability to endure continuous high temperatures, typically up to about 260 degrees Celsius. The materials themselves are strong and lightweight with stable electrical properties. Their intrinsic purity and biocompatibility has enabled widespread adoption as medical implants, for example, in spinal fusion cages. Victrex materials are semi-crystalline thermoplastics, and that means they have a defined melting point. They can be processed by essentially all known melt processing techniques, from extrusion and injection molding through to thermoforming, laminating, and 3D printing. They can also be machined welded, coated, and recycled. At Victrex, we don't just manufacture the polymers, we also make the materials available in various forms, including films, fibers, pipes, powders, fine powders and dispersion coatings, and parts, including composites and selected injection moldings. And as a final point on this slide, I should mention material costs. Everybody asks me this, so I'll start by saying that in general, the cost of these materials on a per kilo basis is higher than the cheaper fluoropolymers like PTFE. In some cases, maybe 2 to 5 times higher. However, costs can be comparable or cheaper than some other fluoropolymers. It all depends what you're replacing and with what. But let's not forget, in the field of high-performance polymers, material replacement is a little bit more complicated than simply looking at price per kilo. And I will return to this point later on. Next slide, please. This slide gives you an overview of some of the application areas where we're seeing interest in fluoropolymer replacement. There are many application-specific requirements which will dictate the detail and the extent to which PEEK can be an effective fluoropolymer replacement, and that's where we can help. What you see on this slide are several common themes emerging in how PEEK performs in each of these applications. In bearings and valves and related equipment, low friction, resistance to wear, and tolerance of temperature are key. In electrical insulation, consistent performance with temperature and time is critical, which is in part derived from the material's purity. That purity also plays a key role in food and pharmaceutical applications, but for different reasons. So, for example, properties like easy sterilizability might be an advantage here. In the food contact area, there are many application opportunities, from 3D components in coffee machines to coatings, for example, in cookware and the food processing industry. And it's once again that combination of properties of our materials which is generating interest in PFAS-free solutions. Next slide, please. Here's some more specific information on what materials are used today in those areas and which Victrex products are either being trialled or indeed already used as fluoropolymer replacements. In valves and seals, etc., various types of PTFE and PCTFE are currently used. Potential replacements include our filled compounds and our PEEK films. For low temperature service, for example, in contact with liquefied natural gas or even hydrogen, cryogenic grades like CT100 are used. Finally, our developing portfolio of lower melting point materials known as LMPAEK are also being considered. For bearings, our primary substitution candidate is the wear grade WG101. This is a product that was developed almost a decade ago as a PFAS-free material, so it's a well-proven and relatively widely used alternative. In wire coating, XPI grades are a range of electrically insulating products with enhanced purity. These are enjoying success in automotive electric vehicle wire and cable applications and in electric motors. For food and water contact, we offer a range of PFAS-free products called FG polymers. These satisfy the requirements for food contact in Europe, the US, and in other territories around the world. And finally, in the pharmaceutical area, we offer some pharmaceutical contact or PC grades, and these are offered both as non-implantable polymers and as extruded films. Next slide, please. So now let's take a quick look at how some of the attributes of PEEK compare with those of some fluoropolymers. I've summarized a lot of information in this table, and I'm not going to go into detail now. This is more for reference purposes, but what you can see is that there's a strong message, a strong overlap between the attributes of Victrex materials and those of fluoropolymers, be that in terms of their mechanical, thermal, and chemical properties or related to wear and electrical performance. And it's these overlaps which are prompting end users to take a fresh look at PEEK materials as potential alternatives to fluoropolymers. Next slide, please. I've summarized on this slide some mechanical properties of some fluoropolymers and PEEK-based materials. It's obvious that there are differences and some are quite considerable. PEEKs are generally stiffer, Young's modulus, and stronger, tensile strength, than some fluoropolymers, especially when filled and reinforced. And this provides big opportunities for weight saving, and I'll come back to that in a moment. Most Victrex materials offer reasonable levels of strain at break or elongation, something which increases considerably as temperature increases. Notice also that some Victrex materials, like our WG grades, can offer coefficients of friction in the same ballpark as some fluoropolymers. And a final but really important point is the density of Victrex materials. Even when filled and reinforced, PEEKs are always much less dense than fluoropolymers. What that means is that for applications where material is being consumed by volume, for example, in molded parts such as seals and seal rings, you need a lot less Victrex material, at constant volume up to 40% less. And then if you take advantage of the higher strength and stiffness I mentioned, there's the opportunity to reduce the weight of parts much further by making them thinner and lighter without compromising the original strength and stiffness. When you put those two factors together, that can have a huge impact on the total cost of the material used in the application. We've worked with customers and seen applications which have achieved weight reductions of between 70 and 80%. When you factor in other factors such as durability, the ability to produce net shape with minimal waste, the potential for recyclability and so on, suddenly the value proposition for moving to a PFAS-free PEEK solution becomes a lot more compelling. And that's exactly what we're seeing from customers and end users today. These are organizations that work with us to extract the maximum value from our materials by realizing that there's more to high-performance polymers than simply the price per kilo. Next slide, please. I'd just like to finish now by saying that if you'd like any further information on any of the materials I've introduced today, please refer to the links here or contact us on our website. Thank you very much for your attention.
Thank you so much, John. And I see that there are quite a number of specific questions about your materials and what they can and cannot do. Their performance. So maybe I'll ask some of it in the Q&A, but there will be a lot of questions for you after this webinar, I'm so sure. Then I would like to hand over to our last speaker, Emil Damgaard Møller. He is a senior consultant at the Danish Technological Institute with a background in materials chemistry. He's working with implementation of sustainable products and technologies in companies with a specific focus on PFAS alternatives. Emil.
Thank you very much. And thank you for the previous speakers for this great introduction. My talk today is gonna be about why it is easy to find a PFAS alternative or fluoropolymer alternative on paper, but it might be very difficult to actually implement it into the products. Next slide, please. Just a little bit about me. I have a materials chemistry background from Aarhus University, and I've been working at the Danish Technological Institute for 3 years. Next slide, please. And I have been working primarily within 3 areas. It's a recycling of wind turbine blades. It's been a little bit of chemical detective work where, you know, production companies find particles in their production that they don't know what is, and they want to understand what it is and if it's dangerous. And then for the past 2 years, I've been mainly focused around PFAS, especially on the PFAS alternatives. Next slide, please. Just to give you a little bit of introduction to DTI, or the Danish Technological Institute, you might know some of these other organizations here. So we are part of this European R&D network and are very close to, for an example, Fraunhofer in our commercial ways. We are not for profit organization, but we are completely self-owned, also meaning that we have no governmental funding in our company. Next slide, please. So to understand why is it's so difficult to actually replace the fluoropolymers in your products, I think it's important that we understand the difference between the word complex and complicated. So a complex problem, that is a problem where we don't know the solution yet. We don't know how to get to the solution. Whereas a complicated problem, well, that would be a brain surgery. It's a very complicated process to do a brain surgery, but if you're properly trained, you know how to do it. And that's the difference between these words. Next slide, please. And what I've seen in my work on replacing PFAS, and especially on the fluoropolymers, is that 10 to 20% of the PFAS uses are complex. We don't know if there's any alternative that will work, not even on paper, and we don't even know how to begin substituting it. Whereas 80 to 90% of all the uses It's complicated. We know how to get there, but it's a very long and difficult process. And I just want to emphasize that we are spending so much time on talking about the complex PFAS issues. We don't know how to replace it in this. We are not going to make the green transition if we are not using fluoropolymers. And I would urge people to actually start out with the complicated cases, meaning that the ones where we know that we'll be able to find a proper substitute and to implement it. And to focus on these as kind of the lowest hanging fruits at the current moment, and then we'll figure out what to do with the remaining 10 to 20%. Next slide, please. I just wanted to give you a very brief materials highlight. This is more for you to have in the slides after the webinar, but if you're looking at the fluoropolymers, I also have a similar one for fluoroelastomers. I see some people asking for that in the Q&A. But if you take the mechanical properties, the chemical resistance, and the temperature resistance, well, if you remove one of these requirements, there is going to be alternatives, again, on paper, that will be viable. You're welcome to use that any way you like after the webinar. Next slide, please. So why is it so difficult? Well, as I already said, finding an alternative for a fluoropolymer or PFAS in your products is not really the difficult part. That's the start of the process. You find an alternative, and finding an alternative on paper is not the costly part. Whereas if you want to implement an alternative in your products, you're going to have quality tests. You're going to verify the materials, especially within the medical device sector. We're talking maybe 7 to 8 years of approval of new materials. So this is the part of the substitution process that are extremely difficult and is extremely expensive. Next slide, please. And therefore, it is so important that we choose the right alternative the first time, because the implementation of an alternative is the expensive part. Now, the biggest problem we have is that we've been using the fluoropolymers for so many years, and every time an engineer has designed a product, if you use PTFE or some of the fluoropolymers, you know it will work. Therefore, it has been used. Now, we have a lot of these alternatives. I mean, you can see from the other presentations here today, there's a lot of available alternatives, but we don't really have the proper track record of the performance of these materials. And this is what I see many of the companies I'm discussing with having the issue with, well, I mean, if we are going to start these long implementation tests for replacements, we are gonna be pretty sure that we have found the right material in the first time. And that's very difficult when you don't have any references to hold it up against. Next, please. So this is kind of why I urge you to get together. I mean, the companies I'm talking to at least are companies having several thousands of different and sometimes hundreds of thousands of components, some of them with PFAS. And if you're going to try to find alternatives for all of these components and parts yourself, you're not going to succeed. This is such a big issue that it's only something that can be solved in collaborations. At least that's my viewpoint. So I just want to introduce you to the PFAS industry collaboration that we are currently gathering. It's not to say, I mean, you're welcome to reach out to me if you want to hear more and if you want to participate, but it's more to kind of inspire you to do similar things with your suppliers and some of your, maybe not competitors, but companies in similar industries. Next, please. So what we see from the companies that we are talking to is that they spend a lot of resources on PFAS. They are scouting for alternatives. It's difficult with the supplier discussions. How do we actually verify new alternatives? We have to navigate ever-changing regulations. I mean, new regulations are popping up all the time, and they are all slightly different. So you have to treat them slightly different as well. Many of these companies have plus 10,000 PFAS components in their product portfolio. And you have a lot of quality concerns about introducing PFAS-free alternatives. Next, please. The goal of collaborating will always be the gearing of investment. So getting together and doing this in an effort together will make sure that each company spend in total less resources and gaining the same amount of information as they would if they had spent 5 times the time themselves. Next, please. And then I think the last part of an industry collaboration is that you have to focus on key but not core components. I mean, we are not going to collaborate about extremely essential components in our products that sets our company aside from our competitors. But I mean, there's a lot of the PFAS components in your products that are there just to make it work. We're talking O-rings, flanges, housings, membranes, all of these standard components that doesn't really set your company aside from others. Next, please. And at least the prerequisites for being a part in our industry collaboration is that you have the mindset that collaborations are the key to solve challenges. It's a willingness to share your experiences and your results from the work that you're doing. We require physical attendance. And then I think the last part is actually the most important in a collaboration, and that's acknowledging that trust is a key factor in a fruitful collaboration. Now, many of you probably have a lot of interventions and, oh, this is never going to work. And if you go to the next slide, I have summarized some of the comments that you probably are sitting with right now. Our products are highly confidential. We can never share anything about them. Nobody has the same specific requirements that we have in our products. We are probably going to do most of the work while the other participants are profiting from our knowledge and hard work. We are way ahead in our PFAS efforts compared to other companies. We will not share with the world that we're using PFAS. Therefore, all of our efforts must be kept internally. And we see it as a huge competitive advantage to be first on the market with PFAS-free alternatives. I don't think I have the time to answer all of these questions here today, but these are the inventions that I meet when I talk with other companies, and we have solutions to all of them. And these are not questions that we should use to not join a collaboration or collaborate with each other, but it's something that we have to address before we start collaborating. Next slide, please. With that, I just want to say thank you, and let's keep in touch. You are very welcome to reach out to me if you're interested in participating in an industry collaboration about PFAS. And then I hope I gave you a little bit of insights to why it's not as easy as it seems on paper when finding PFAS-free alternatives. Thank you very much.
Thank you so much, Emil. That's very encouraging to hear anyway, that there are so many solutions to be found, and great to hear about your collaboration as well. I would invite everyone in the panel to switch on your cameras because we are going into the Q&A sessions. I can tell you already, I don't know, let's see, Ian and John, if you could turn on your cameras, that would be great. Perfect, thank you. So there is a variety of questions and we won't be able to address all of them naturally. Quite a number of quite technical questions for you, John. And I'll try to lump them a little bit together and you'll just let us know if you're comfortable with answering them. So there are several questions about the ecotoxicity of PEEK and PEEK. And they're asking what tests have been done in order to avoid regrettable substitution, and many other questions related to this. So could you talk about the hazardousness of your materials? That would be great.
So our material is generally regarded as non-hazardous. There are no ecotoxicity issues of which we are aware. And it's been around for quite some considerable time, and as a testament to its purity and durability, I would highlight the fact that it's been used in human medical implants for over 20 years without a single reported problem.
Okay, thank you for clearing that out. And if you have further questions about that, then please contact Victrex afterwards. Maybe for an even more technical question, because we do get quite some questions about, for instance, flexibility of the peak performance. So how does peak perform in terms of flexibility in relation to the needs of the transport sector, in this case, was a question, or smaller equipment requiring significant amount of cables with a high degree of compaction? I don't know if you're able to answer this on the spot, but if you can, it would be appreciated.
Yes, I can. I mean, PEEK's been used for decades in wire and cable insulation in the nuclear industry, in the automotive industry, in the oil and gas industry as a material that is flexible. It's used in the hairpins in EV vehicle motors. So you can see once it's coated on a wire, it is extremely flexible. And of course, we offer PEEK not only as a granule that can be coated onto wires and then flex, but we also offer it in a flexible format with our film product range as well.
Thank you. And then we get a number of questions, many relating to textiles, and I'm not sure, Ian, if you're prepared to answer this, but I'll just shout it out anyway. They ask if there are any forms of silicones or silicone-based polymers that can be used as replacements, especially in films that must withstand high temperatures, and then specific questions about textiles. And I would also, before you answer that, in any case, refer to another webinar that we had a few months back in this webinar series about technical textiles, where you will find a few of these alternatives being presented. But Ian, do you think you could elaborate on it?
In the context of textiles, probably not, because it wasn't
well, both, actually. So if it's not textiles, that's okay as well, because they weren't all about textiles.
I mean, and these specific areas of use are covered quite extensively in the Eco Restriction Report. There's a very extensive section of the Eco Restriction Report on textiles specifically, where obviously alternatives there are discussed quite extensively. So I think I would probably point people in that direction for that. And in terms of, so what was the first area of use you were covering?
Let me double check. Especially in films that must withstand high temperatures.
Well, I mean, within the context of what we were looking at in this particular project, one of the areas of complexity we had was that you can have certain uses within one of these individual sectors, be it industry or transport, or even medical and green energy uses, where the types of materials you need only require a certain level of temperature resistance or chemical resistance, and in other contexts it would need to withstand much harsher conditions. And so the use of a particular product or a particular material for a particular use within these sectors can be very, very different depending on the different contexts. So yes, temperature resistance is a very important factor within polymer uses in general. Within the context of these particular uses, you can have obviously the specific nuances around a particular application is very different. So it really does depend on exactly which particular application you're talking about, or the context of it that you're using, depending on what the temperature quality you need is for a particular material. So it's very difficult for us to answer on the basis of what we were looking at for this particular project, because it was taking quite a generalized look.
Yes.
So yeah, one of our overall kind of conclusions is if you want to get up to the real crux of those kinds of answers, you do need to look very specifically at the application or the function level, rather than just at the area of a broad sector, or even a subsector within a broad sector.
Great, thank you. And I think that maybe, John, maybe you have had the opportunity to scroll through the more technical questions that come in around your alternatives. Would you be able to address maybe a few of them now that you've looked through them?
Yes, of course. Yeah, I noticed there's a couple of questions that have come up about PFAS, whether PEEK contains PFAS, whether PFAS is used in its manufacture. So there's an opportunity just to be very clear on this. When we make PEEK, we do not use PFAS in its manufacture, in its polymerization. When we extrude PEEK into films, fibers, compounds, and other things that we manufacture, we do not use PFAS as processing aids for extrusion in those processes. A couple of questioners referenced a particular paper of which I'm aware. That paper actually contains some factual inaccuracies because it does claim that PFAS, including fluoropolymers, are used for extrusion during plastics production. That is incorrect as far as Victrex is concerned. In fact, we have actually sent a number of our materials for independent third-party laboratory analysis. Quite an extensive study that analysed our materials looking for pretty much every PFAS that exists out there in the OECD list. And in every case, there was no PFAS detectable in our materials down to levels of 10 parts per billion.
Great, thank you for clarifying that. That's great that you had some time to look through the different technical questions that maybe I don't even understand. We have one question on a more policy level that I would like to ask Hannah. It says, my US colleagues tell me that the definition of PFAS is not the same in the US. Specifically, EPA definition does not include F-gas refrigerants like HFCs, HFOs. How accepted is the definition of PFAS used in Europe?
Okay, so I can try and answer that. I don't know the US definition at all, actually, but the PFAS definition that is used in the European restriction dossier, the universal one, is based on the OECD definition. And the OECD made a new PFAS definition in 2021, which is stated as PFAS are defined as fluorinated substances that contain at least one fully fluorinated methyl or methylene carbon atom without any HCl chromium or iodine atom attached to it. And then the restriction dossier takes that definition and removes a few PFAS from it that are seen as degradable. And this means that, for example, some F-gases are not defined as PFAS. So I'm not sure if there is a discrepancy here, but the OECD definition is globally recognized. So there might be discrepancies between regulatory contexts, but this is widely acceptable, I would say, as a definition.
Yeah, thank you.
But it's fairly new, so it's from 2021. That can cause a bit of confusion that the definition has changed over time.
And I believe that is why the dossier submitter did use that definition, because it was widely acknowledged. So I think we should leave the Q&A now. You do have more questions and you'll be able to come back to the speakers, and we will also have a look at the questions to see if there is some work ahead where we can clarify these things. There is one specific question, if the report from WSP is available on our website. It's not yet, but it will be. So with that, I want to kind of summarize what we talked about today and the general conclusion. And I mean, the PFAS pollution crisis is here, and the contamination is global. The extreme persistency makes this contamination different to any of the pollution problems that we've dealt with before. There is just no way around restricting all the uses, and this includes the fluoropolymers. That's very important to state, because the problem is not going away, and we are passing it on to future generations indefinitely. And the longer we wait, the more we accept continued use when there are alternatives available, and when it's not critical use, the more we increase future costs and harm to citizen and to the environment. So for fluoropolymers, as for so many specific applications, there is no drop-in alternative that can replace all the functionalities at once, and that's okay. It just means that we need to look harder. We need to be more granular and specific on what properties it is that we actually think are critical, not what's nice to have. And we don't have all the answers, like Ian said, to all applications, but we have some, and it's clearly not impossible. There are these materials that are fit for the future, This is competitiveness. So with that, I want to thank the speakers so much today. You had great presentations and good answers also to all these different questions that I posed to you. And I also want to take the opportunity to tell you that our next webinar in this series is already set to the 6th of November, when we will talk about mobile air conditioning. So I hope to see you all then, and thank you very much for today. Bye-bye.